Welcome everyone. The title of today's notes is Systems of Linear Equations in Two Variables. This represents the beginning of a new unit here where we're going to be looking at a variety of systems of equations and systems of inequalities. So today you'll probably see a lot of overlap from Algebra 1, but there's some prerequisite skills that we want to solidify before moving forward. So just make sure you're able to kind of do some of the things that we accomplished today. You'll see some substitution and elimination. And again, a lot of that should be review from what you've seen before. But perfect that arithmetic. Make sure it's absolutely perfect there as we go ahead and take those next steps forward over the next several notes worksheets. So anyway, let's kind of start it out here. Looks like on your notes, it does say something along the lines of system of linear equations, and then obviously we're going to be solving a system, so we'll talk about that solution in just a sec. But let's get this going here. On your paper, if you could write this in, that would be outstanding. So really, when we talk about a system, it's just more than one equation. So what I have is essentially it's a collection of two or more, and in this case, since they're linear systems, then they're going to be linear equations. All right, perfect. Now again, what I'm going to do is say solve the system, and so what that solution is going to be, it would really represent the values of the variables, and because we're talking about a linear system in two variables, we'll talk about x and y, so the values of the variables that really make both equations true. And so as we all know, if we're talking about a line on the coordinate plane, a line has an infinite number of ordered pairs, and as a result, an infinite number of values that would make the equation true. If we're talking about more than one now, if we're talking about two lines on the coordinate plane, we're going to want to find that ordered pair that makes both equations true, really that fits on both lines. So we'll take a look at this graphically for just a second here. It looks like on your paper it says something like 3 scenarios for linear systems with two variables. The first one will by far be the most prevalent one that we see, and then the other two just variations that we'll see every now and again, really very infrequently. So here's what I'll ask you to do, everyone. If you can go ahead and just give me 3 coordinate planes side by side. And again, we're really talking about how lines can be dealt with on the coordinate plane. And so if we're talking about a system of linear equations, we're talking about 2 in this case. Basically the most, as I said, prevalent way that this would occur is you would have an infinite number of ordered pairs on that line, and as a result, an infinite number of x's and y's that would make the equation true. And if you have a second one, maybe something like this, also, again, an infinite number of points on that line, an infinite number of x's and y's that would make the equation true. If we're looking for the solution to the system, obviously we're looking for the one where it would make both true. And so that would be the point of intersection. And again, that's the one we're going to see most often. So intersecting lines, basically, and actually I'm going to write that below here. So one way graphically that we would see this is 2 lines intersecting on the coordinate plane. So intersecting lines, and of course, we would get one solution out of it. And that one solution would have an x value and a y value. Don't forget that piece. Now, other ways that we can graph lines on the coordinate plane, as we can see in that first case, they intersected. Well, here's a line right here. What happens if I have my other line and it's parallel? So if I have a situation like that, well, again, there are an infinite number of points on this line. There are an infinite number of points on this line. But it just so happens there aren't any points on both. There's not a single x and y value that would make both equations true. So in this case, again, don't see this very often, but of course, kind of know what to look for here. So parallel lines. And of course, this case, there would be no solutions. So not every system is going to have a nice ordered pair that works. All right, so that's the second. And again, as I mentioned, the second and the third kind of go hand in hand here. Let's see what the third would look like. I guess here would be graphing one equation on the coordinate plane. And so it would produce a line, again, an infinite number of solutions, et cetera, et cetera. In this particular case, what happens if the next equation actually produces the exact same line? something like that. So two equations, just so happens all the ordered pairs for the first equation are the same for all the ordered pairs of the second equation. Well, yeah, again, we can kind of call this an infinite number of solutions. Sometimes you'll see textbooks call it many solutions. Not a big fan of that, but I'm going to write it here anyway. And so basically what that would mean, and if you write this down, that's perfectly fine. It's not that big of a deal. But basically what we would characterize it as there are an infinite number of solutions, and it would be all of the points on that particular line. They happen to be the same line. So actually I should have put this above. So let me just switch that order there. And this would be really two equations producing the same line. And we would call it many solutions. I guess if we wanted to be more specific, it would be the infinite number of solutions on the line such and such, y equals mx plus b, whatever it may be. Okay, we don't want to say just infinite number of solutions, because I think that would maybe imply that it could be any x and y value. But obviously it can't be any x and y value. These points don't work in them. It's just really the points on the line. And yes, there are an infinite number of points, but we would be a little more descriptive about it. Okay, so this is somewhat of a cop-out, to be honest, but you can go with it, and that's perfectly fine. So as I mentioned, it's really this one that we'll be seeing most often here. And so kind of get used to that piece. Others we'll take a look at in due time. All right, well, let's keep it moving here. Again, what we're going to see is a variety of methods. As a matter of fact, we're going to explore at least 4 or 5 methods to solve a linear system of equations. And the first two, I would say, are definitely reviews from Algebra 1, substitution and elimination. I just threw my 2 cents in maybe when you would want to use one as opposed to the other. But truth be told, you do whatever you'd like in terms of whichever works best for you. If you like substitution, if you just see that a little better, then go for it. If you like elimination, you see that a little better, then go for it. I'll just ask us to get a little practice on each one there. So I will specify one way or the other here. But again, on a test or on your homework or on a take-home quiz or anything like that, it'll just be like solve the system and do it however you're going to do it. So substitution versus elimination. So in this case, I'm going to start with substitution. We'll get a little practice on this. I'm going to go through it relatively fast just because I know this is such a review from Algebra 1. If for, again, whatever reason you're just not sure of something, slow it down a little, pause and rewind and kind of go back and take a look and ask questions, of course, if you have them. So substitution, we've talked about this strategy a little bit before, but if we're going to substitute, we will sort of want to get one variable by itself. And I would argue that this y down on the bottom here is the easiest to get by itself. All I have to do is bring that 2x on over to the other side. So I'm hoping everybody sees that y is equivalent to 2x plus 7. I do a lot of circling and drawing into where it would go, so I'm going to circle that 2x plus 7. And if you remember correctly, basically, if that is equivalent to y, then it can replace the y in the other equation. Just make sure you do it to the other equation. Now, this actually brings up a good point as to kind of why this works and why we want to do this. Remember your goal when you solve a 2-by-2 system, which is exactly what we're doing here. Our goal is to really break the system down from 2 equations and 2 variables, which is exactly what I see on the board here, down to 1 equation and 1 variable. That we can solve. And so when I substitute this expression 2x plus 7 in for y, I get exactly what I want. I got my 2x, and instead of minus 3y, it's minus 3 times 2x plus 7. And as a result, you see that essentially my first objective has been satisfied. I have 1 equation, 1 variable, and now we should be able to solve. So again, everyone at this stage, if you can go ahead and start the solution process here, you can work a step ahead of me if you'd like. When I combine the 2x and the minus 6x, and I'll go ahead and do that, I guess. So minus 21 equals negative 13. And again, it just looks like negative 4x. I'm going to bring that 21 on over to the other side and get that right there. So again, just good arithmetic dealing with solving these nice 1-step, 2-step, 3-step linear equations, and you get your first variable. All righty, perfect. So just remember, that's a great first step. You've got half the solution set that you want. Sometimes I do this just when I get that first one, I immediately put it in just to get me thinking about the fact that I do need the second one. And then, again, you can circle here. I'm not going to circle it because I don't want things to get too convoluted. But basically, I would take that -2 at this point, find a place to put it in for x so you can solve for y. I would think the most ideal spot is probably right in here. You already know y is equal to 2 times the x plus the 7. And so I guess in reality, we get something like this. And then it looks like y is equal to +3. So -2, +3. If I graphed both those equations on the coordinate plane, that would be the point of intersection. If I put -2 back in for x and I put +3 back in for y, in each of those equations, it should balance it. It's the only ordered pair that balances both. Okay, great. Let's go ahead and get a little more reinforcement on this. I'm just going to do example 2. Again, if you feel comfortable with this, great. That's exactly the intention here. If you're struggling with any of this, please slow it down, go back and take a look, and just perfect the arithmetic. That's the key. The next notes worksheet deals with 3 equations and 3 variables, and it's not the concepts that I'm worried about with those. It's the execution piece, and we'll talk about that on the next notes worksheet. All right, let's go get 2. I would definitely say that top y is the one we probably want to get by itself. If it's okay with you, I'm probably just going to bring that over to the other side. And when I do, I get y equals 3x there, so actually not too bad at all. Again, just a habit that I get into is I circle it and I draw it to where it needs to go. So 4x, 3 times 3x, and then equals 26. Okay, and then let's solve together here. It looks like I have 13x equals 26. And x equals 2. So nicely done. I like that piece where just getting it down to one equation, one variable, and that should be a good comfort zone for us. So I've got this going. It is 2 for the x value, and let's put it back in. And again, this is sort of the place that I see it. Y is equal to 3 times x, 3 times 2, and so it should be 2 comma 6. Okay, great. And okay, let's move forward then, and let's get into the next piece, do some elimination here. So if you remember elimination, it's another way to go down from 2 equations, 2 variables, to 1 equation and 1 variable. And essentially this occurs when you add the system together. And so example 3 really illustrates this as easy as it gets. So what I'm going to ask you to do right away, and we'll talk about why, just put a plus out in front, and what we're going to do is add the system. And this is all based on equality, of course. Since these 2 are the same, and these 2 are the same, I can add this to this, and it's the same as adding this to this. Everything is in equilibrium, and so as a result, I can add one to the other and still keep everything balanced perfectly. And so when I do add the system here, I do get a 4x and a 2x. There's our 6x. And here's sort of the scenario that we were looking for. The 2y and the -2y, when I add them, I get 0 y's. So they become eliminated, so to speak. And 14 and 10 make the 24. And now notice what we have. We have 1 equation in 1 variable, which is exactly what we wanted. And now, of course, we can just solve. Oops, I made a mistake there. So let me go on back and solve with relative ease and end up getting x equals 4. Good. Now remember, just that's half the battle, of course. That worked out really nicely here. I have x equals 4. I would plug it back in. It doesn't matter where you find a spot, but basically x is 4, and the y is the unknown at this point. And so what we want to do is just make sure we solve correctly. And notice, just nice and careful with that arithmetic, everybody. Go through that process. Sometimes, and you'll see this with the 3x3s, if you struggle with the arithmetic piece, if you make one mistake, obviously the rest of the problem just goes kablooey there. So just be careful. And it's sometimes tough for a teacher if you come up and say, hey, I'm not sure where I made a mistake. Sometimes it's like a needle in a haystack for me. So take your time with it, relax with it, and you should be okay. So anyway, before I ramble too much there, 4, -1 seems like the solution just by elimination there. Now we go to example 4, and same situation, but in this case, before I put a plus out in front and a line underneath, would adding the system make sense here at this point? Well, if I add these 2, well, nothing cancels. If I add these two, well, nothing cancels. So it wouldn't benefit us to go ahead and put a plus out in front right now. What we want to do, as you saw on example 3, let me come back to it, is you have coefficients one on top of the other that are opposites, a positive 2 and a negative 2 in front of those y's. So that's what we want to do. We want to create opposite coefficients here. And I'm hoping everybody sees this piece, again, as a review from Algebra 1, that if we multiply that top equation by 2, that should allow us to get this going. So the way I'll just play it out, I like rewriting it. Just make sure that the only mistake I typically see with this is forgetting to multiply the entire equation by 2. So 2x and 6y and 24, that is an equivalent equation. Again, as long as I do something to one side and balance it out on the other, it's still okay. So now I'm ready to roll with this. I add those two together, and those are going to cancel, and 10y equals 20, and of course everyone y equals 2. Perfect. Now again, just find a spot. It really makes no difference. All you need to do is put in the 2 for the y and make sure you're able to solve for x. I'm just going to throw it into the original top, but 3 times 2, and n equals 12, and so x plus 6 equals 12. And x equals 6. Alrighty. Good, so I've got 6 comma 2 and all said and done there. And notice numbers are working out fine. They won't always, but just as long as you're careful with your with everything you do there, should work out nicely. Just check, double check. Again, I like these problems because really you can find out if you got it right or wrong based on just plugging it back in. If you got it right, great, you move on, feeling good. If you got it wrong, well, obviously then you have to go back and either restart the process or find your little mistake there. Okay, let's try one more elimination and then again just go through a few pieces here. We'll skip maybe a couple towards the end, but let's just make sure at least I'm presenting everything you need to know and that you're kind of getting a little practice here and then getting some more practice on your own. So same situation on this one. I might have to kind of work over to the side here, but basically what I see is we don't have opposite coefficients just yet here. So we can either create opposite coefficients in front of the x's or the y's. You can't go wrong, your choice. Just think about multiples of 3 and 2 or multiples of 11 and 5. I guess 3 and 2 work out pretty well here. If I multiply that top equation by 2, I'll get a 6x out in front, which would mean I do want a negative 6x down on the bottom there. And so if I just multiply that by 3, that should suffice. So again, just create opposite coefficients. That's the bottom line. And I'm sure with your knowledge of multiples shouldn't be a big deal. So let's see what I have going here. Looks like here's my negative 6x minus the 15y, and 27 would do. I'm going to add now, and 6x's should cancel out. And it looks like I get a 7y and 35, so the y is equal to 5. Very nicely done. Again, all you have to do is find a spot to put it, solve for the remaining variable. Over the years, I've seen students actually kind of stop right there, so just be a little careful on that. Obviously, finish the entire problem. So let's see what unfolds here. I get 3x and 55 equals 4. 3x, bring over that 55, everyone, and looks like it's negative 51, and I'm getting a negative 17 on that piece. And again, if we're not sure about anything at all, if we feel like, oh, we're not entirely confident that that's the answer, well, obviously, guys, all you have to do is put the negative 17 and the positive 5 back into the original 2. And if it's the only ordered pair that balances both, you've got it. All right, so negative 17 and 5. Okay, so that's just substitution and elimination. Kind of get those skills taken care of. I don't expect you to really remember all the things with the 3x3s, which we'll see on the next notes worksheet. But in order to do those 3x3s, really this, as I said, has to be pretty perfected. Let's take a look at a couple variations and applications of these two variables. So it just says solve by substitution or elimination here. I'm just going to go by elimination if that's all right with you, probably for both of them. And it just sort of says what happens to both variables, what is the resulting equation, true or false, and as a result, what would be our solution set there. So watch what unfolds in this case. And again, if you're a step ahead of me, that's fine. I would probably just go ahead and multiply that bottom equation by -2. And when I do that, I get the 6x, 2y equals 7, and I get a negative 6x and a minus 2y, and then equals negative 4. And so if I look at this particular case, when I put a plus out in front, well, again, the x's get eliminated and the y's get eliminated. So I guess in reality, that entire left-hand side, when I add those together, I have nothing. I have 0. Everything sort of balances out to just getting back to 0. But the other side, I have 7 and negative 4. And then I get something that says this. So let's, I guess, answer a couple of the questions that I have on your sheet, and then we can sort of interpret what's going on. It says, what happens to both variables? Both get eliminated. So our goal is to eliminate one, and in this case, both of them become eliminated. And then it says, is the resulting equation true or false? And as you can see, all I have is something that says 0 is equal to 3, and that simply is not true. And so as a result, no matter what I put in for x and y, I get a statement that is really not true, not numerically correct. And so no matter what happens here, I can never get that equation to balance out and be true. So it says, what is the answer? Well, essentially, this would be the no solutions that we saw on the front side. And so if, and again, if we were to graph these on the coordinate plane and saw the visual perspective on this, we would see that they would form parallel lines on the coordinate plane. And so if they don't intersect, there are no x's and y's that are going to balance both equations. So this is the no solution situation. You could probably guess what's going to happen here, but let's play it all the way through. So I'm going to do it one more time, everybody. I'm going to, let's see, multiply this by 3, it looks like. And so what's interesting here, I get 9x minus 3y equals 12. And bear with me on this. It looks like a negative 9x and a plus 3y equals negative 12. And same thing, I add. What happens on this side? Well, both get eliminated, and so I'm left with 0. And then on the other side of the equation, when I added those together, I end up getting 0. So let's, again, answer the questions here. And you could probably guess what's happening. But both get eliminated. Just a consequence of trying to eliminate one accidentally eliminated the other. Is the resulting equation true or false? Well, it's true. 0 does equal 0. So we do have to be a little careful here. It's not that I can put in any x and y values and have them work. It's all the x's and y values for this particular line, because as we can see, everyone, it's just the same line, just by the way it was written initially, just multiplied by a different factor. And so this is what we called many solutions. As I said, we can dive deeper into this, but to be honest, I don't really care too much about that piece. So let's just write in many solutions there. But theoretically, it would represent all of the points on, maybe you would write something like all of the points on the line 3x minus 4, or something like that. And there are an infinite number of points on that line. That essentially would be our solution set. All of the points on this particular line. If you want to cop out a little bit and do this many solutions, that's fine. Again, for our purposes, it's not that important. Perfect. Well, guys, just as I said, most of them will be one solution, kind of like what you saw up here, but there are those two other variations, of course. All righty, let's go to this last piece. Couple applications here. I'll tell you what, let's cross out example 8. I think we can let that go. Example 9, why don't we just do a setup here, and then we'll do example 10. So I'll tell you what, for example 9, why don't you read through it for a moment, and just see if you can set up 2 equations and 2 variables. We're going to be doing that, especially towards the end of the unit, trying to work through a word problem and translate it mathematically. There's a context that we're going to see where that's going to happen. For right now, just a fairly straightforward one. If you can just write a system, 2 equations, 2 variables, and then we won't go through the whole process of solving. I'll just go ahead and give you the solution set. If you want to solve it, of course, you're more than welcome to. So I'll read it quickly, and then as I'm reading, maybe you're writing, we'll see what happens. So a hotel has 200 rooms. Those with kitchen facilities rent for $100 per night, and those without kitchen facilities rent for $80 per night. On a night when the hotel was completely occupied, revenues were $17,000. How many of each type of room does the hotel have? So just one thing to note here, and this is just a good habit to get into, nothing more. But if we're going to set up a system of equations, we should probably define our variables. We'll talk about that when it does get harder. But I would say X is the number of kitchen facility rooms. Excuse my shorthand there. And Y would be the number of I guess that's the best way to say it, non-kitchen facility rooms. So again, if we do that piece, maybe it allows us to write our system of equations a little easier. Not a necessity at this point, but a good habit to develop. So again, I've been rambling now a couple minutes. Maybe you've paused the video or not, but essentially I think we're looking at the number of rooms added together would be 200, so X plus Y equals 200. And then in terms of the revenue, it looks like the revenues totaled $17,000. Where did that revenue come from? Well, it looks like each kitchen facility room brought in $100, so 100 times the number of kitchen facility rooms. And then the revenue also was made from the number of non-kitchen facility rooms, and each one of those brought in $80, so 80 times the number of rooms. And if you solve that, let's see if I have this on my paper here. Yeah, I have something, so we'll go 50 and 150 if you solved. Perfect. Okay, now the last one I do like, so we'll take it all the way through. We're going to do a lot of work with quadratic functions over the course of the year, and this just says find a quadratic equation. And this is the standard form of a quadratic equation. One thing is missing, by the way, just something out in front, so we'll see a variation on this in the near future. But for right now, it would be y equals 1x squared plus bx, b being a coefficient, plus c, so c being a constant on the back, and for a parabola that passes through 2 points here, 4, 4, and -3 and 11. And if you get an opportunity, and I think we kind of know this intuitively working with equations, basically, again, if it is a point on the graph of the function, then it would make the equation true. So we can use it to plug in for x and y. And that's exactly what I'm going to do. I'm going to take that 4 and 4, put it in for x and y. I'm going to take that -3 and 11, put it in for x and y. And so let's see what happens when we do that. And it looks like the 4 is the y when the 4 is the x. So I end up getting 4 squared. I'm going to switch the order there, 4b. And plus c. And then the other one, well, the 11 is the y when the -3 is the x. So just be a little careful on that -3 squared. And then minus 3b, and then plus c. Just make sure you see that piece. All I did was use those two x and y values and put them in the equation. And when I did it the first time and got a single equation in 2 variables, b and c being the variables that we want to solve for. And then I did it a second time, and as you can see, I have a secondary equation with the same 2 variables. 2 equations, 2 variables, now we should be able to solve. So let's clean that up just a little bit here. This will be 16, and I'm going to bring that over to the other side. And then this will be 9, and I'm going to bring that over to the other side. So guys, I'm going to have to come up here, see if you have some room with this. But if I bring that 16 on over, I get -12 equals, and then 4b plus c. And if in this case, when I bring the 9 over, it looks like I get 2 equals -3b, and same deal, plus c. So let's solve this together. I don't have a problem with that. Either substitution or elimination there. And if it's okay with you guys, I'm going to maybe even do like 2 steps at once. I'm going to multiply that bottom equation by -1 in order to get these two to be opposite coefficients, a positive 1c and a negative 1c. And then in the same breath, and again, if you get an opportunity to do this, great. If you need to rewrite it and add the system separately, that's fine, of course. But I see if we were to add the system, this would be -12 times now -2, and should get -14 on that. This will be a 4b and really a positive 3b at this point. And so this would be 7b, and then those would eliminate. So as you can see here, b is now -2. And if we put in that -2 in for b, then we should be able to come up with the c value accordingly. So let's see what happens when we do that, kind of the last step here. Find a spot to put in that -2. I'm going to just put it in that top. So 4 times -2 and plus the c. Again, just really getting that habit. When you have one variable, should be able to find the other. And this would be negative 8, so I'm going to add 8 to both sides here, and negative 12 plus 8 should be negative 4. And that's my C value. So what this is basically saying is there is a certain parabola that'll go through these 2 points that fits this mold right here. What would be the B and C value on that equation to pull that off? And let's go ahead and write it. So let's see, I have y equals x squared, and how about a minus 2x and a minus 4? So this would be the quadratic equation that produces a parabola going through those 2 points right there. If I put 4 and 4 in, so 4 in for x, I would get 4 in for y. If I put negative 3 in for x, I should get 11 for y. That's the equation that would do it. All right, so a good one. We're going to see a harder variation on this coming up in the next couple of notes worksheets, but a 2x2 really not too bad. All right, as I mentioned with this one, just make sure you're really comfortable with substitution and elimination. We're going to pick it up and do 3x3s on the next notes worksheet. And again, I'm not too worried about the concept. I know you can handle that. It's the execution aspect of it. Well, if you have any questions along the way, please don't hesitate to ask. And thank you very much for listening, of course.